Acid strength. So electrolytes are substances that form ions in aqueous solution, right? And the strength of an electrolyte, whether it's strong or weak, depends on how much it ionizes, the extent of its dissociation into ions. So a strong electrolyte dissociates completely. Weak electrolytes only dissociate a little bit. And electrolyte has to do with the solution will conduct electricity because it has ions that can move and carry the electrical current. The strength of an acid depends on an equilibrium. So we have this equilibrium between the acid and its conjugate base, water acting as a base, and a conjugate acid. So if this is a strong acid, that means it's also a strong electrolyte, and this reaction essentially goes to completion. It ionizes completely. A weak acid is a weak electrolyte. It will only ionize partially, and so this will be an equilibrium with both sides having significant concentrations. Does that make sense? When we talk about strong acid, we need to be careful not to get that confused with how corrosive the solution is. So you can have an extremely dilute solution of hydrochloric acid. It's a strong acid. Is it dangerous? No. No, it isn't. A weak solution of a strong acid is fine. Orange juice is probably more dangerous. So strong does not mean dangerous. Strong means it ionizes completely. You could also have a very concentrated solution of a weak acid, and it could be extremely dangerous. So weak and strong has nothing to do with how corrosive the substances are. It has to do with the extent of ionization. So there are 6 important strong acids, and you need to memorize them. We need to know which are the strong acids. All the other acids are assumed to be weak. So we memorize these 6, and then everything else, if it's not one of the 6, it's weak. So we've got hydrochloric acid, hydrobromic acid, and hydroiodic acid. These are the hydrogen halides. HF is not in the group. For those who haven't had me for 1A, I think of the halogens as being sisters. They're in the same family, right? So you've got fluorine, chlorine, bromine, and iodine. Fluorine is the littlest sister. She's the smallest. She's not part of a strong acid. It's the 3 older sisters, HCl, HBr, and HI. So those are strong. And then these guys, and you just figure out a way, I guess. I remember them because I've been doing this, and I don't have a trick for this one. Nitric acid, perchloric acid, and sulfuric acid. Those are the strong acids. We also need to be familiar with these terms: monoprotic, diprotic, and triprotic. That says how many ionizable hydrogens are there, how many protons that could be donated. Monoprotic, 1 ionizable hydrogen. So most of these strong acids are monoprotic, but sulfuric acid is a diprotic acid. It has 2 hydrogen ions that can be donated. It does not donate them both at the same time. It donates 1, becoming hydrogen sulfate ion, and then it can donate the second one. Sulfuric acid is strong in its first ionization, but not in the second. You can also have triprotic acids like phosphoric acid, H3PO4, has 3 protons. Any questions? There's something to add to your flashcards. So strong acids, like HCl, there are virtually no intact HCl molecules. So we've got the single arrow instead of the equilibrium arrow. This goes to completion. You look in the solution, there are no intact HCl molecules. They are all separated into ions. So if we have a 1.0 molar HCl solution, then the concentration of hydronium ion there is going to be 1.0 molar. Because what happens to the hydrogen from the HCl? The hydrogen ion. The thing ionizes, forming hydrogen ions, and that hydrogen ion immediately finds a water molecule to hang out on, forming a hydronium ion. All of the HCl ionizes, all of the hydrogens in there become hydronium ions. So for strong acids, the concentration of hydronium ion is the same as the concentration of the acid. A weak acid like HF, fluorine, the little sister in that family, only ionizes partially. So when we write out this equation here, we've got HF reacting with water, but we have equilibrium arrows because this is definitely going both ways. There are hydronium ions and fluoride ions present, but we also have a significant number of HF molecules present in the solution. It doesn't ionize completely. So here we've got a bunch of HF molecules in the solution along with ions. So if we're looking at concentration of hydronium ion for a 1 molar HF solution, the hydronium ion concentration is going to be a lot less than that because only a portion of the HF molecules ionize. Does that make sense? So how strong an acid is depends on the attraction between the conjugate base and the hydrogen ion relative to the attractions of those ions to water. So if you have a strong acid, there is a very weak attraction between the hydrogen ion and the anion, the conjugate base. They would prefer to be with water. So this will form hydronium ions, and this anion is also interacting with the water molecules. That's that ion dipole force where the water molecules come around anions or cations and solvate them. And so these guys would prefer to be apart in a strong acid. In a weak acid, there's a much stronger attraction between the hydrogen ion and its conjugate base. And so many of them will remain together, only some of them will separate. So the stronger the acid is, the weaker the conjugate base is. If we have a strong acid, here, this is the conjugate base, right? Strong acid will go completely to the right. In order for this to act as a conjugate base, it has to reverse, right? The reverse reaction happens almost zero. And so it is an extremely weak conjugate base. So the strength of an acid and its conjugate base are inverse. If one's strong, that means the other's weak. So how do we measure what's going on with that equilibrium? Oh, maybe we should use an equilibrium constant. Right? So we learned about this in chapter 15. So the acid ionization constant, Ka, this is the equilibrium constant for the ionization of a weak acid. So we're going to talk about the acid ionizing to form its conjugate base. So here we have the acid plus water. It forms hydronium ion and the conjugate base. We write the expression exactly the same as for the other equilibriums that we looked at. You take the product concentrations and divide by the reactant concentration, again with exponents equal to the coefficients. So we can write it this way where we're looking at hydronium ion, or we can write it this way where we're dealing with hydrogen ions, but we understand that those hydrogen ions are actually on a water molecule. We're just ignoring the water. When you do this equilibrium, in the denominator, you would have H2O liquid, right? I'm lost. My pointer and I are not communicating. Would H2O liquid be included in the equilibrium constant expression? No, because a pure liquid cannot change its concentration. So liquids, solids are excluded. And so it's actually, let me force it. Come on. Okay. It's actually easier to just use hydrogen ion here instead of writing out the hydronium ion. So a large Ka means that the equilibrium goes far to the right. So the larger the equilibrium constant, the stronger the acid, right? If you have a small equilibrium constant, that means that the reaction does not proceed very far, and you have a weak acid. Does that make sense? Large Ka, stronger acid. So this is a table of some acid ionization constants, some Kas, for some monoprotic weak acids. And they specify the temperature because equilibrium constants change with temperature. So you may need to refer to a chart like this to find a Ka value. And over here, we have pKa values listed. And those are related. Those are just like pHs. We'll talk about that in a minute. So on this table, they're showing you in red what the ionizable hydrogen is. They're giving you structural formulas, and then they're also giving you the ionization reactions.